Good evening, all. I welcome you all for the week 4 live interactive session for the course Chemical Reaction Engineering 2. Now, let's get on to the session. So, we'll get into the session. So, as usual, we'll have a brief recap of the lectures of week 5. The week 5 had 5 lectures, of which the first 3 lectures were on internal effectiveness factor, and the fourth lecture of the week was on falsification of kinetics, and the last lecture for the week was on external mass transport limitations, where mass transfer coefficient was defined. Uh, in the first lecture, the derivation of the internal effectiveness factor for a spherical catalyst was derived. It was derived for both first order reaction and for an nth order reaction, and it was found that um, when Thiele modulus is very small, the effectiveness factor is almost a constant, and in this region, the surface reaction control dominates, and as the Thiele modulus goes large and large, the effectiveness factor has an inverse relationship with that of the Thiele modulus, and this region is more of a internal diffusion controlled reaction, and in between these two region is a region where both the surface reaction as well as the internal diffusion controls the reaction. If in the lecture 22, the same internal effectiveness factor was derived for a slab catalyst, and it was observed that the trend of the curve for internal effectiveness factor versus the Thiele modulus remains almost similar for across the geometries, and then the internal effectiveness factor accompanied by a volume change was discussed in the same lecture. In lecture 23, what happens in the case of a non-isothermal reaction? What happens to the internal effectiveness factor for a no, for non-isothermal condition was discussed, and the concept of multiple steady state was identified. And in lecture 24, the falsification of kinetics. What is the kinetics we derive? We are able to identify based on the parameters that can be measured. For example, the bulk concentration can be measured, whereas what is happening on the surface or inside the catalyst, that concentration cannot be measured. So based on that, we derive a kinetics, but this kinetics is not the actual kinetics what is happening within the catalyst, whereas it varies by a certain factor. And what is that factor in case of an order, for activation energy, and for a frequency factor of the rate constant, were all defined and derived. And the last lecture of the week initiated on external mass transport limitation. So as we know that the catalytic reaction is a 7-stage process, where the first and last stage are the external mass transport process involving external mass transport, where in the stage 1 there is an external mass transport, there is an external mass transport from of the reactant from the bulk onto the catalyst surface, And similarly, in the state 7, there is an external mass transport or the bulk mass transport of the products from the catalyst surface to the bulk. So, what happens in the case when external mass transport limits the reaction rate? So, that was defined, and initially a model equation where the mass transfer happens from a bulk to the surface without any reaction happening was derived, and the mass transfer coefficient was estimated. So the equation was written based on the uh, driving force by resistance, where your resistance is nothing but your inverse of your mass transport coefficient. Now, let's get on to the practice assignment of uh, week 4. Question number 1. The reaction A gives B is carried out isothermally on a porous catalyst. The intrinsic reaction rate is given by K into Ca square, where K is the rate constant and Ca is the concentration of A. If the reaction is strongly pore-diffusion controlled, the observed order of the reaction is it 1 or is it 2 or is it 3 by 2 or is it root 2? So which of these is the right option? This is a GATE 2022 question. So we have certain information from the question that the observed reaction rate is a second order reaction, right? And one more information is that it is strongly pore diffusion control. That means the internal diffusion controls the kinetics of the reaction. So it is a major rate controlling parameter. Now we are supposed to find out what is the they've given the intrinsic reaction rate as a second order kinetics, and they are asking what is the observed reaction rate. Okay, so we can find this out based on the falsification. You know, the formula derived from falsification of kinetics, right? So we have the relation. So the apparent order n prime and the actual order n is defined as n. So given the given parameter is uh, actual order, that is the intrinsic reaction rate, which is 2. It is second order with respect to the reactant A, because it is given as Ca square. That means order is 2. Now the relationship between the apparent order and the actual order is given by n prime is equal to n plus 1 by 2. So incorporating what is the value of n, you will get 2 plus 1 by 2, that is equal to 1.5, which means option C 3 by 2 is the right answer. Now let's get on to the question 2. Sorry. So let's get on to the question 2. A catalyst slab of half thickness L, the width and length of the slab are very much larger compared to the thickness, is used to conduct first order reaction A gives B. At 450 Kelvin, the Thiele modulus for the system is 0.5. The activation energy for the first order rate constant is 100 kJ per mole. The effective diffusivity of the reactant in the slab can be assumed to be independent of temperature, and external mass transfer resistance can be neglected. If the temperature of the reaction is increased to 470 Kelvin, then the effectiveness factor at 470 Kelvin is what will be the effectiveness factor? So the value of universal gas constant R is equal to 8.314 joule per mole Kelvin. So what have they given? They have given, they are using a slab catalyst. And then the Thiele modulus for conducting a first order reaction. So the reaction is of first order, and the Thiele modulus for this first order reaction at 450 Kelvin is 0.5. And they have also given the activation energy E for this reaction, which is equal to 100 kilojoule per mole. And the next information is that the effective diffusivity dE is not dependent on temperature. So whether it is going to be 450 Kelvin or 470 Kelvin, the dE is not going to change. And similarly, there is no external mass transfer resistance. And they have asked us to determine the effectiveness factor at 470 Kelvin. Now, so given first order reaction, so T1 is 450, T2 is 470 Kelvin, Phi1 is 0.5. E is 100 kilojoule per mole. R is 8.314 joule per mole Kelvin. Now D is independent of T, and the reaction rate constant can be given as, it's a Arrhenius relation, right? So K is equal to K naught into exponential of minus E by RT, where K naught is the frequency factor and E is your activation energy, R is the universal gas constant, and T is the temperature. Now at T1, K1 will be K naught into exponential of minus E by R T1, because your activation energy and your your frequency factor are not going to change. These two are constant, and at temperature T2, K2 will be K naught into exponential of minus E by R T2. So now, if we take a ratio of K2 by K1, the exponential, the ratio of the rate constants at the two temperatures T2 and T1. So K2 by K1 will be equal to minus E by R into 1 by T2 minus 1 by T1. So we have all the values of E we have, and then we have the value for R, and we have for T2, and we have the value for T1. So from this and here again I have converted E, which was in kilojoules per mole, to joules by multiplying by 1000 to maintain the unit consistency. So we end up with the ratio of the two rate constants at different temperatures, K2 by K1 is equal to 3.1186. We know that for a first order reaction, Thiele modulus is given by L into square root of K by dE, where L is the characteristic length and K is the reaction rate constant and dE is the effective diffusivity. Now, if we take the ratio of phi2 by phi1 for both the temperatures, then you will end up with L into square root of K2 by dE divided by L into square root of K1 by dE. So which is equal to square root of K2 by K1. Why is it so? Because your characteristic length is not going to change. It is the same catalyst. The characteristic length is going to be the same. Similarly, they have given that this effective diffusivity is constant with respect to temperature, or is independent of temperature. So eliminating both, cancelling both, you will end up with square root of so phi2 by phi1 is equal to square root of K2 by K1, which is equal to square root of 3.1186. So you already have the value of phi1, which is nothing but 0.5. So you can find out what is phi2. So phi2 is equal to 0.883. Now phi2 is equal to 0.883. So for now we have to find out what is the effectiveness factor for the temperature 470 Kelvin. For a slab geometry, it has been derived in lecture 22 that the effectiveness factor is given by tan hyperbolic of phi divided by phi. So now we have for the case 2 where the temperature is 470 Kelvin. So we also have what is the value of phi 2, which is nothing but 0.883. Incorporating that, what you will end up with, so eta 2 is equal to tan hyperbolic of 0.883 divided by 0.883. So your eta 2 is equal to 0.8017. Next, question number 3. The overall rates of an isothermal catalytic reaction using spherical catalyst particles of diameters 1 mm and 2 mm are Ra1 and Ra2. Their units is mole per kilogram catalyst per hour respectively. The other physical properties of the catalyst particles are identical. If the pore diffusion resistance is very high, then what is the ratio of the reaction rates when the diameter of the particle is 2 mm to the reaction rate when the diameter of particle is 1 mm? That is Ra2 by what is the ratio of Ra2 by Ra1. So this is again a GATE question which was asked in GATE 2013. So how do we proceed with the solution? So we know that diameter D1 is 1 mm. So the corresponding radius is 0.5 mm. And D2 is 2 mm. The corresponding radius is 1 mm. Now we have to write the rate equation. So rate equation Ra is equal to eta into RAS. How did I get at this? So it is based on the effectiveness factor. So effectiveness factor is given by the actual rate by divided by the rate where all the parameters like concentration, temperature are all equal to the surface conditions. So just rewriting it, you will get the actual rate Ra is equal to eta into RAS. So we know what is RAS. RAS is nothing but Kn into CAS power n. Right? Now we can write the ratio of Ra2 by Ra1 as, so eta 2 Kn2 CAS2 power n2 by eta 1 Kn1 CAS1 power n1. Now, assuming the intrinsic reaction rate constant, order and concentration does not change with the diameter. So, all these are all constant. What you will end up with is your the ratios of the reaction rates is equal to eta 2 by eta 1. So, we are assuming that in both the cases, the surface concentration is the same. The reaction rate, the intrinsic reaction rate, the order of the reaction is the same, and the reaction rate constant is also same. So that's why you end up with Ra2 by Ra1 is equal to eta 2 by eta 1. Now, for a pore diffusion control for a spherical catalyst, your eta is nothing but 3 by phi n1 into root of 2 by n plus 1. 3 by 5 into square root of 2 by n plus 1. Because for a spherical catalyst, since there is a pore diffusion, you don't have any this the cottage term, because it this effectiveness factor comes as a inverse, just with an inverse relation, that is it is 3 by 5. For example, in case of the first order reaction, it will be eta is equal to 3 by 5, and for the nth order reaction, it is equal to 3 by 5n into square root of 2 by n plus 1, where n is the order of the reaction. Now, eta 2 by eta 1 is equal to, since we have assumed that the order is the same for both the cases, So your this term will go off. Your square root of 2 by n plus 1 will go off, and your term 3 will also get cancelled, and you will end up with eta 2 by eta 1 is equal to phi n1 by phi n2. Now bringing in the formula for Thiele modulus. So phi is equal to r into square root of k by dE. Now given all the other catalyst parameters are equal, that means your your reaction rate constant and your effective diffusivity, everything is constant, and only your radius is varying. That means Ra2 by Ra1 is equal to eta 2 by eta 1, which is equal to phi n1 by phi n2, which is nothing but equal to r1 by r2. So your r1 is 0.5 and your r2 is 1. That means the ratio of the reaction rates is 0.5. So if we observe that when the diameter of the particle is increased from 1 mm to 2 mm, the reaction rate has decreased because your Ra2 is 0.5 times of Ra1. In the case of the pore diffusion control. Okay. Now let's go on to question number 4. So question number 4 is, for a first order catalytic reaction, the Thiele modulus phi of a spherical pellet is defined as phi is equal to Rs by 3 into square root of K into rho P by dE, where rho P is the pellet density, dE is the effective diffusivity, Rs is the pellet radius, and K is the first order reaction rate constant. If phi is greater than phi, then the apparent activation energy is related to the intrinsic or to true activation energy as, is it related as EA is equal to E power 0.5, or is it EA is equal to 0.5 into E, or is it EA is equal to 2 times of E, or is it EA is equal to E square, where EA is your apparent activation energy and E is your true activation energy. So one thing you have to look into is phi is kind of very large, so it means kind of pore diffusion controlled. Now the answer is actually EA is equal to 0.5 into E. This is derived in the class for falsification of activation energy, where your reaction rate is given by minus Ra is equal to 3 by R into square root of 2 by n plus 1 into square root of dE into square root of at into exponential of minus E by RT into CAS power n plus 1 by 2. So it's nothing but your theta into minus RAS. From there you just derive in, and this is nothing but your square root of K. So which is equal to 3 by R into square root of 2 by n plus 1 into square root of dE into at power half exponential of minus E by 2 RT. Because this square root inside exponential, it has become E by 2 RT into CAS power n plus 1 by 2, which is nothing but equivalent to the apparent kinetics, that is equal to Kn prime into CAS power n prime. So that is nothing but apparent frequency factor into exponential of minus apparent activation energy by RT into CAS power n prime. So if you just look into the activation energy term, so RT is same. So here it is EA, whereas here it is E by 2. That means E apparent is equal to E by 2. That is nothing but 0.5 times of E. And similarly, your apparent frequency factor, if you just compare, here your AT apparent is equal to this whole term. It is 3 by r into square root of 2 by n plus 1 into square root of dE into AT uh, square root of AT here, which is nothing but your actual frequency factor. So this is what is the relation. Now moving on to question number 5. This is again asked in GATE 2007. The first order reaction of A giving R is run in an experimental mixed flow reactor. Find the role played by pore diffusion in the run given below, where Ca0 is 100 and W is fixed. Agitation was found to have no effect on the conversion. So, what is given? Your diameter of the particle, so your catalyst particle is given, and your Fa0 is given. Okay, molar flow rate is given, and your conversion is given. So in the first case, the diameter is 4, your Fa0 is 2, and your conversion is 0.8. In the second case, your diameter is 6, whereas your Fa0 is 4 and your conversion is 0.4. So they have asked whether in this scenario, is it a pore diffusion control, or is it diffusion free, or is it intermediate role by pore diffusion, or is it external mass transfer that is controlling the reaction. Now, the answer here is pore diffusion control. How is it pore diffusion control? From the data, we can observe that as the diameter of the particle increases, the conversion is decreasing. Right? So, the diameter is 4, the conversion is 0.8, whereas the diameter is 6, the conversion is 0.4. Right? So, we just saw in the previous problem that your reaction rate, it decreases if your pore diameter increases. So applying that. So that is what I have also mentioned with respect to the Thiele modulus. So Thiele modulus, you have this, relationship where it, it gives the ratio of surface reaction rate to the diffusion rate. And your Thiele modulus is proportional to R when all other parameters are constant. So for the first case, it is proportional to 4. Second case, it is proportional to 8. So then the Thiele modulus increases with R, which implies that the diffusion rate decreases with R. So as a diameter, of the catalyst pore, it increases, your diffusion rate, it actually decreases. Okay. Now, because the diffusion rate is in the, as we can observe, the diffusion rate is in the denominator. Okay. Now, question number 6. A packed bed reactor converts A to R by first order reaction with 9 mm pellets in the strong pore diffusion regime to 63.2% level. If 18 mm pellets are used, what is the conversion? So, looking into the problem, we can see that, they have changed the pellet diameter. They have increased the pellet diameter. So, one clue we get is that the conversion is going to decrease. Okay, because your diffusion rate is inversely proportional to the Thiele modulus. Okay, and Thiele modulus varies directly as the characteristic length. So with these two information, we can get an idea that the conversion is going to be less compared to that of your for the conversion, sorry, for in case of 18 mm pellets, your conversion is going to be lesser compared to your 9 mm pellets. So what is the information given? So as usual, they have given the diameter, that is 9 mm, and the radius is equal to 4.5 mm, and the diameter 2 is 18 mm and your radius is 9 mm. So conversion they have given, so XA1 they have given it as 0.632. So what is XA2? So again they have already given that it is a strong pore diffusion regime. So they have also given it is a first order reaction. So eta is equal to, for strong pore diffusion, when Thiele modulus values are very large, then your effectiveness factor varies as 3 by 5 for the first order reaction, and phi is given by R into square root of K by dE, where K is your reaction rate constant and dE is your effective diffusivity and R is your radius. Now, how to find the conversion? So here we have to use the design equation for a packed bed reactor in line to a PEFR. So your design equation is dXA by dW is equal to minus RA prime by FA naught. So rearranging it, you will get dXA by minus RA prime is equal to dW by FA naught. And then incorporating what is RA prime. So minus dXA by eta into K into Ca naught into 1 minus Xa is equal to dW by Fa naught. So here what we have done basically is that we have expressed the reaction rate happening in terms of these surface reaction, when the condition is in terms of surface reaction multiplied by the effectiveness factor eta. So we have taken as eta is equal to minus RA by minus RAS. So minus RA is equal to eta into minus RAS. So that is what we have done. And then we have to integrate the above equation. Once we integrate the above equation, you will get minus ln of 1 minus Xa is equal to W into eta into K into Ca naught by Fa naught. So now taking the ratios for the two different diameters, you will get minus ln 1 minus Xa2 by minus ln 1 minus Xa1 is equal to W into eta into K into Ca naught by Fa naught for the case 2 where the diameter is 18 mm divided by W eta into K into Ca naught by Fa naught where the diameter is 9 mm. And then cancelling out the other terms which we can assume as constants, you will get the ratio of ln of 1 minus Xa2 by ln of 1 minus Xa1 is equal to eta 2 by eta 1, which is equal to 3 by phi 2 by 3 by phi 1, which is nothing but phi 1 by phi 2. And then incorporating the formula for the Thiele modulus, which is nothing but R into square root of K by dE. Here again K and dE are constant in both the cases, so those cancel out and you will end up with R1 by R2 is equal to 4.5 by 9, that is equal to 0.5. Once we get this, then ln of 1 minus Xa2 is equal to 0.5 into ln of 1 minus 0.635. So substituting, we have substituted all the values. So just mathematical calculations, you will end up with Xa2 is equal to 0.3959. This is what is the conversion. So the conversion has decreased with the increase in the radius of the pellet. Now next question. For a first order reaction having a positive volume expansion, the effectiveness factor after volume expansion is greater than the effectiveness factor before volume, without volume expansion. That is, eta prime is greater than eta. Is it true? Identify if the statement is true. So they have given that the reaction is first order, and this first order reaction is having some expansion. Say for example, consider a gaseous reaction where A gives B plus C. So here in the total moles in the products is higher than that of the total moles in the reactants, right? That means there is an expansion. So there is a positive volume expansion. That is what it means. So for this positive volume expansion, so volume expansion you will get it by from the term epsilon. So V is equal to 1 plus epsilon into V naught. So the effectiveness factor, uh, they've said that the effectiveness factor after the volume expansion is greater than the effectiveness factor without the volume expansion. So is it true for the case? The answer is false. It is not true for the case. It is actually the effectiveness factor after the volume expansion is less than that of the effectiveness factor without the volume expansion. How? So if we just look into the graph of this volume expansion to eta prime by eta, we can see for various Thiele modulus values, for a negative value, you can find that eta prime is greater than eta. Whereas as a epsilon value, goes towards positive values, then you can find that the ratios are smaller. So eta prime, it just falls below 1, right? So that means eta prime should be less than eta. So that is what is the actual scenario. Okay. Now let's discuss the final question for this week. A catalyst is chosen for a particular non-isothermal reaction, that melts beyond the surface temperature Ts. So there is a catalyst they have chosen for some particular non-isothermal reaction, and this catalyst, what happens is that this catalyst starts melting if the temperature of the system goes beyond the surface temperature. That is the surface temperature of the system at the catalyst surface, I'm saying. So is the choice of the catalyst right under all circumstances. So whether can we go with this catalyst for this kind of a reaction under all circumstance, or does it have any impact that the melting beyond the surface temperature is having any impact? So what is the answer is that no, we cannot choose this catalyst which melts beyond the surface temperature of the reaction, catalyst surface temperature. Why? Because the choice of catalyst that melts after Ts is not the right choice for all the cases of non-isothermal reaction. So we have to, if it is a isothermal reaction, then your temperature is not going to change, not much change in the temperature. So the Ts will be maintained. Whereas for a non-isothermal reaction, what happens is that the local temperature within the catalyst can reach far beyond the surface temperature. So what happens in this case? The local temperature within the catalyst, it might increase. Since it is a non-isothermal reaction, it might increase within the catalyst surface. Okay. So within the catalyst, that means the catalyst will start melting and there will be loss of catalyst. If the temperature shoots up beyond this Ts, it will start melting and you will lose the catalyst and your total process is stopped with the loss of catalyst as well. Okay. So that is the answer. So why is it this scenario? So as discussed in the non-isothermal effectiveness factor, so your effectiveness factor for a non-isothermal condition becomes a function of beta and gamma, where beta is your temperature difference, the maximum. So it is the T max minus Ts, the surface temperature by Ts, and your gamma is E by Rts, which is nothing but your Arrhenius activation energy with the surface temperature. I mean, the Arrhenius factor, the surface temperature. So, there is a discussion that what happens. So, we will get into unsteady, so multiple steady states. for if your Thiele modulus is at certain values. Say for example, in this case, at point 1, you could see that it has two steady states. Okay. And there will be cases where there will be three steady states. So there might be some steady states which are unstable, and the system tends to shift towards the other. And in this process, the temperature might shoot up when it falls, and also there is a possibility that the reaction goes runaway. That is, the temperature becomes uncontrollable, and your the whole system is collapsed. So this is the reason we have to choose the right catalyst, and we have to check into this beta and gamma factors when it comes to non-isothermal reaction. So this is it with this week's practice assignment. Thank you.